All right. Can anyone confirm whether I'm audible? Can anyone confirm whether I'm audible? Students? Can anyone confirm whether I'm audible? Yes. All right. Good evening, all. Welcome you all to the MCQ discussion of circular motion. So I'm going to start. Others will join meanwhile. Right. So since anyway it's a YouTube live, I'll start because if anyone needs to go back and see, they can still go back and see the live. Right. Yes. Okay. Thanks. Thanks. Right. So we'll start. We'll start. And for the tute for today's session, if you are in any of our groups, right, you can go to the groups and download it, or else now from the live chat, I have pinned a message. I have pinned a message uh, saying the link for tute, right? So you can visit that link and get the tute first, right? So I hope you have downloaded the tute. So if you haven't downloaded the tute yet, I have pinned the message in the chat box. So you can go to that chat box and you can see the pinned message there. Right? From that, visit that link I have uh, put to that. Visit that link, and from there you can download the soft copy of the tute. Right? So please download it and get ready for the session. Right? I'll give you like 1 minute to download the tute if there's anyone who didn't download the tute yet. Right? All right. All right. So listen first. The main focus of today's session is discussing. Here I have given you 20 MCQs. Discussing these 20 MCQs on circular motion, and these 20 MCQs cover different types of circular motion questions that have been uh, come in past papers. Right? There are calculation type questions, statement type questions, logics. Everything is there. So as it covers everything, I have put these questions. So we'll start, right? So we'll start. I guess all of you have downloaded the tute, and now you are ready for the discussion, right? Question 1. A particle moving in a circle of radius 2 meters at constant speed has a period of rotation 2 seconds. Period. Period is periodic time. Its acceleration towards the center of the circle is. So we know if there's an object which undergoes a circular motion, it has an acceleration towards center. That is called centripetal acceleration. So what they ask is about centripetal acceleration, right? And the period is given. Okay, look at here. Look at here. So we know equation of centripetal acceleration. Equation of centripetal acceleration is either v squared dou r or r omega squared. Equation of centripetal acceleration is AC, centripetal acceleration, v squared dou r or r omega squared. Right? Since period is given, we can go with omega expansion because period is inside omega. So from this, A equals r omega squared. But we know omega is 2 phi over t. Omega is 2 phi over t. Therefore, A can be written as r omega squared will be 4 phi squared over t squared. Omega squared will be 4 phi squared over t squared. Now hereafter, this is just a matter of substituting. So let's substitute these values. R is given 2 meters, 4, and answers are given in 5 squared. So keep it like this. Keep it like that. And t is 2 seconds. 2 seconds, which means this is 4. T squared is 4. Right? Now these two cancels. these two cancels. Now you can see A is 2 phi squared. So that is a velocity, that is an acceleration. So that is in ms minus 2. That is an acceleration. So that is in ms minus 2. Right? So first question, answer is 2 phi squared ms minus 2. Answer 4. Answer 4. 2 phi squared ms minus 2. Answer 4. I'll mention the answers here as well. For first one, answer is 4. For first one, answer is 4. Right? Take it down and make corrections quickly if you have anything. If you have any changes, if you have anything to be taken down from this, you can do it quickly. And if you have tried these questions already, you can mark your corrections. If they are correct, you can mark whether they are correct or not. Here we have 20 MCQs. So by checking these 20 MCQs, we can make sure whether in which level are you in circular motion, right? Because this covers everything in circular motion. Take it down quickly if there's anything. Take it down quickly. Okay. Okay, let's move on to the second question. Question 2. Question 2. Two particles A and B are moving in concentric circles. Concentric in the sense it has the same center, common center. Concentric means they has concentric means they have common center. Concentric circles of radii RA and RB such that their periods of rotation are same. Periods of rotation are same. The ratio centripetal acceleration of A to centripetal acceleration of B is right. Then look at here, concentric circles. So something like this. If they are concentric circles, so let's say first one is RA and this one is RB. So they move in two concentric circles like this. They move in two concentric circles like this. Two concentric circles. Right? Such that their periods of rotation are same. Now again, periods are same. Period is periodic time. Periodic times are same. Right? The ratio of centripetal acceleration. Okay. Then let's write down this way. A to B, no? Then for A, if I check this, see, for A, centripetal acceleration of A is, let's say AA, can be written as R omega squared, no? Because centripetal acceleration is R omega squared. Now, if I expand this in terms of T, omega is 2 phi over T. Omega is 2 phi over T. Right? So, therefore, A can be written as R 4 phi squared over T squared. R 4 phi squared over T squared. Now, I'm going to use this equation for A and B separately. See, I'm going to use this equation for A and B separately. This is for A. For A, we can write RA 4 phi squared T squared. Right? Let's consider period dash T, that is common, that is given. And if I use the equation for B, right? Centripetal acceleration of B equals RB 4 phi squared T squared over T squared. Right? Now what we need is centripetal acceleration of A to B. This ratio, see, A of A to A of B. So divide these two. Divide these two. From first one, RA 4 phi squared over E squared. Divide this. Division is multiplication with reciprocal. Right? So RB 4 phi squared. Division is the multiplication with reciprocal. P squared to P squared cancels. 4 phi squared to 4 phi squared cancels. Right? So final answer equals RA over RB. So which means the ratio of accelerations are RA over RB. Answer is 1. RA over RB. For second one, answer is 1. For second one, answer is 1. Okay. So quickly take it down if there's anything. Quickly take it down if there's anything. Okay, we are moving on. Next one. Question 3. Question 3. A small mass is kept on a horizontal circular table, which can rotate about a vertical axis passing through its center of the table. The mass starts to slip when the angular velocity of the table becomes omega. The mass starts to slip, right? When angular velocity becomes omega. If the distance of the mass from the center of the table is doubled, the minimum angular velocity required for the mass to start slipping is, right? So let's have a small diagram first. So that is on a table. Okay. In first scenario, get here. In first scenario, it is kept at a distance r from the table, and if there is a rough table only, this can be this can be the mass start slip. Yeah, if there is rotating without slipping, which means the table is rough, right? If the table is rough, we have friction forces towards the table. So this is friction. We have friction forces towards the table. So first we can apply F equals ma towards center, considering this motion, and get the equation. And then they are saying that if the distance to the mass from the center of the table is doubled, minimum angular velocity required. Okay. See, towards center, we can use F equals ma. Towards center, F equals ma. So which means simple F equals m r omega squared. Simple m equals m r omega squared. Right? So let's consider this as equation 1. Right? And second instance, at the second instance, if the distance to the mass from center is doubled, right? But still, friction remains same because friction is mu r. If mu remains same, and if reaction remains same, reaction depends on mg. If mg remains same and mu remains same, because that's the same table, nature of the surface is same, friction is same, right? And for second scenario, we can do the same. Then F equals m, instead of r, we have 2r, right? So let's say omega dash squared. That is scenario 2. Right? Now, if we need that velocity, we can equate these two. There are many options. Either you can divide or you can equate, right? Anything is fine. So I'm going to equate these two. 1 equals 2. From 1, mr omega squared. From 2, m 2r omega dash squared. Right? Omega dash squared. M to M cancels. R to R cancels. They're asking omega dash. No? So subject omega dash squared equals omega squared over 2. Subject omega dash is omega over root 2. Omega dash is omega over root 2. Omega over root 2, answer 1. Answer 1. And students, you can raise any question in the chat box, right? So you can raise anything that you have through the chat box. Doesn't matter whether you are a regular class student or if you are a newcomer here, it doesn't matter. You can always question if you have anything. You can always question if you have anything. And if that is not clear or if you have any kind of a doubt, I welcome all of your questions, right? I welcome all of your questions. Is it clear enough? Is it clear? Is it clear? So you can respond to my questions through the chat box as well, right? So if it's clear, say clear. If that is not clear, you can ask me to explain again. Then I can explain again, right? So I hope it's clear enough. Okay, good. Moving on. Moving on. Next. Time is enough, no? Can you explain it again? Look at here. Listen here. It says a mass is on a table, and when the angular velocity becomes omega, it starts slipping. So which means at the very point it becomes omega, that is at the equilibrium. And if there is a little bit greater than omega, that starts slipping. So therefore, I have written the equation, I have applied the equation for the point which starts slipping, right? So just before that point, it is in the circular motion like this. So it undergoes the circular motion just before slipping. Just before slipping, it undergoes circular motion. So therefore, considering that, use F equals ma towards center. Towards center, the only force it has is F. And let's consider omega as this direction. Direction doesn't matter. Direction doesn't matter. Same answer comes, right? So F equals ma, and A can be expanded as A of circular motion can be expanded as R omega squared. A of any circular motion can be expanded as R omega squared. So then F equals mr omega squared. And in the second scenario, the distance is only doubled, right? Distance is only doubled. F is a friction, no? This is a friction force. This is a friction. This is a friction, right? So friction depends on mu r because F equals mu r, and mu depends on nature of the surface. Same table and same object, so mu remains same. And r depends on mg. R depends on weight. Same object, same weight. So therefore, friction is same. Now again, considering that for the second scenario also, I use the same equation. F equals ma towards center. F equals m. This is actually F equals ma towards center. This is F equals ma towards center again. So F remains as F, mass is same, distance is doubled, right? And new omega I consider as omega dash. Since F and F are equal, equate these two, and subject omega dash, they are asking omega dash, right? Minimum angular velocity required to start slipping, omega over root 2. Now is it clear? The one who asked the question, Hafeel, is it clear enough? So likewise, any one of you can ask questions if there is anything that you don't get, right? So we are moving on. Question 4. Question 4. A horizontal table is rotating with a uniform angular velocity about the vertical axis passing through its center. A mass simple m is at rest on the table without slipping. Observer A is sitting on the table while the observer B is standing on the floor, as shown in the figure. The total horizontal force on M. Okay, total horizontal force on M. Now we have to see this. We have to see this as a relative motion, because the reason is one person, that is actually capital A, is on the table. Right? Now listen. This is a good question. This is a good statement question. This is a good statement question. Right? Listen. Now, with respect to A, first let's discuss about A. With respect to A is on the same table itself. Now, that mass M is somewhere here and A is somewhere here. So, both rotate at once like this. Both rotate at once. So, therefore, there is no relative motion of simple M with respect to A. Because A is also rotating with the same angular velocity, same speed. Right? So, therefore, there's no relative motion between A and M. Therefore, what A sees as M is at rest, right? So with respect to A, see, between A and M, no relative motion, no relative motion. No relative motion means what he sees is as M is at rest. What he sees is as M is at rest, because there's no relative motion there. There's no relative motion. Right? So therefore, according to A, there's no force, because if there is at rest, no force. If there is at rest, force is zero. If there is at rest, force is zero. So therefore, according to A, there is no force acting on simple M. Now let's go to B. B is on ground. B is on ground, right? It is given as B is standing on the floor. B is standing on the floor. B is an outside system, right? So therefore, B sees that simple M rotates, simple M undergoes a circular motion. That B sees, right? So B sees that simple M undergoes a circular motion. So therefore, between B and M, there's a relative motion. That is a relative motion. Right? That is a relative motion. So therefore, B sees that it undergoes in a circular motion. So B sees the circular motion. So that is actually the circular motion. So if there is a circular motion, we all know that there's a centripetal force on any object which undergoes in a circular motion, right? So therefore, since for B it's sensitive as a circular motion, right? So he know that there's a centripetal force acting on that, right? So therefore, centripetal force is visible. Centripetal force. Therefore, centripetal force is visible, right? Again, between B and M, there's a relative motion, right? Relative motion in the sense what B sees M is undergoing in a circular motion, right? Because B is at flow. What B sees is M is undergoing in a circular motion. Since there is a circular motion, so we know that there should be a centripetal force for that circular motion. So therefore, he understood and we can see that there's a centripetal force on the object. Right? Centripetal force always acts towards center, right? We all know that direction of centripetal force is towards center. So therefore, according to A, force is zero. According to B, centripetal force no, that is towards center. According to A, zero, and according to B is towards the center. Answer is one. Answer is one. For four, answer one. For four, answer one. So this is the explanation. That is a good statement question. That is a good statement question as a combination between circular motion and relative motion. A combination between circular motion and relative motion. Is it clear enough, students? Students, is it clear enough? Is it clear enough? You can ask if there's anything you don't get, right? You can ask if you have anything that you don't get. Now, by the end of this session, right? If you can clarify all your doubts you have about circular motion, and if you can fine tune your skill in circular motion, that's the whole intention behind this. So therefore, uh, you can ask any questions if you have. Right? No questions. No? We are moving on. Question 5. Question 5. An object moves along a horizontal circular path on the inner surface of a smooth conical shaped vessel. Conical shaped vessel, as shown in the figure. The forces acting on the object as observed by a stationary observer is. Right. So this is the motion. A conical shaped vessel. Right. And so the object is somewhere here. Object is somewhere here. Right. On the wall. Object is on the wall. Right. Now, forces acting on this object are, right? Forces acting on this object are mgx. Other than that, a perpendicular reaction acts. Other than that, a perpendicular reaction acts. Right? About centripetal force, right? Now, center is here. Look at here. Center is here. So one component of this comes as centripetal force, and the other component counterbalances mg. Right? So one component of this comes as centripetal force, right? This is centripetal force, and this counterbalances mg. This counterbalances mg, right? Now, as observed by a person here, no? As observed by a person here, right? Uh, mg can be seen by this person. Mg can be seen, and r is also visible. R is also visible, right? Because if there is in contact with the wall, r is also visible. And about the centripetal force, uh, exactly a component of r acts here as centripetal force. A component of r acts here as centripetal force. So therefore, if that person can see this resultant, this reaction force there, right? We can see the reaction force now, which means we don't need to say centripetal force again, because then it's going to be duplicated. It's going to be duplicated, and simply always keep in mind that centripetal force can only be felt by the objects which undergo circular motion, right? Otherwise, when it comes to an outside system like this, they can't see or they can't feel centripetal force, because centripetal force is a force which acts on objects which undergo circular motion, right? So therefore, it can be felt only by the object it undergoes circular motion, right? So therefore, this person don't know whether that there's a centripetal force here as well, right? And again, about R, the argument is about R. The argument is, since he can see the contact, he know that there's a reaction, right? This person can see the contact now. This person can see the contact, so he know that there's a reaction, right? He know that there's a reaction. Now, in reality, a component of this reaction acts as centripetal force. So therefore, we can't use two forces like perpendicular reaction and centripetal force, because actually the component of reaction acts as centripetal force. Another component of reaction counterbalances mg here. Another component of reaction counterbalances mg here, right? So therefore, let's go to the answers. Weight of the body only. No. Weight of the body can be seen, and other than that, in addition to that, R can also be seen. R is also visible. Weight of the body, weight of the object, and reaction force normal to the surface only. That is correct. That is correct. Weight of the object and reaction force normal to the surface only. That is correct. Right? And other answers are weight of the object and centripetal force. No, centripetal force cannot be seen. Only this can be as centripetal force. Reaction force normal to surface and centripetal force. No. Centripetal force. No. Answer is 2. Weight of the object and reaction force normal to surface only. Answer is answer 2. Question 5. Answer 2. Take it down and ask if you have anything to clarify. Take it down and you can ask if you have anything to clarify. Is it all good? Is it all good and all clear? Students, is it all clear? Now, this is again a good statement question again, right? Question 5. That's again a good statement question. Good statement question. You can download the route from the pinned message, right? For the ones who joined late, you can download the route from the pinned message in the chat box. Okay, moving on. Question 6. Question 6. A child of mass 20 kilograms is sitting on a string of negligible mass. The string is attached to its pivot by 2 ropes, each of 3 meters length. Each of 3 meters length. Something like this. Right? A string. And actually here we have 2 ropes. 2 ropes. And the child is like this. 3 meters length. The maximum speed of child during a swing is found to be 3 ms minus 1. Maximum speed. The maximum tension in each rope piece. The maximum tension in each rope piece. Right. So first thing, first argument we have to use is the maximum speed of the swing. The maximum speed of the swing occurs at the lowest point. Right. The maximum speed occurs at the lowest point, right? First point is maximum speed is at lowest point. Maximum speed is at lowest point. So therefore, my interested point is this now. My interested point is this. 20 kilograms means his weight is 200 newtons, and the respective tension has to be tension here, right? T and T. Now what we can do is simply we can use F equals ma towards center, right? Towards center. Towards center, F equals ma. F is T minus 200. F is T minus 200. And M is 20 times speed is given. No? So A can be expanded as A equals V squared over R. A equals V squared over R. Then V squared is 3 times 3 over R is also 3. Right? Simplify this. So T minus 200 equals 60. T equals 260. But this is not the final answer. This is not the final answer. The reason is it says it has two ropes. Now I have got the total tension as 260. Total tension is 260, right? So therefore, tension on each. Therefore, tension on each rope. Therefore, tension on each rope equals T over 2, that is 130 newtons. Tension on each rope is 130 because this 260 is the total. This is the total. It is total tension. That is total tension. Clearly, the question asks, right? In the last line, you can see. In the last line, you can see clearly the question asks the maximum tension in each rope is. The maximum tension in each rope is each rope, right? So therefore, total is 260. Tension in each rope is 130. Take it down. Take it down. Okay, next one. Next one. Question 7. So for question 6, what was the answer? Answer 1. Question 6, answer 1. Question 6, answer 1. Question 7. A toy car connected to a fixed point by an elastic string as shown in the figure travels in a horizontal circle of radius 2r. The initial unstretched length of the elastic string is r. The period of rotation of the car is t. The car is then speeded up until it's moving in a circle of radius 3r. If the string obeys Hooke's law and resistive forces are negligible, the new period of rotation of the car will be right. So if there's anyone who don't know Hooke's law, Hooke's law actually comes in waves and oscillations. So that is coming up in our next unit, right? That is in unit 3, right? So therefore, I'll explain what Hooke's law is. Hooke's law says F equals Kx. See, Hooke's law says F equals Kx. F is force and K elastic constant or spring constant, elastic constant, or we call it spring constant. Spring constant, and X is called extension. Extension. So this is called Hooke's law. This is called Hooke's law. This is called Hooke's law. Okay, now we can use F equals ma towards center, considering car, right? So simply F equals ma towards center. That's it. Using F equals ma towards center. Using F equals ma towards center. Only force acts on this is F, right? F. So it can be expanded as Kx. I'll expand at once. Kx. And they are asking about period. So therefore, expand A as r omega square. Expand A as r omega square. mr omega square. Right? And we know omega is 2 pi over capital T. So therefore, Kx can be written as mr omega squared is 4 5 squared over t squared. Right. Now, if we are asked about, since we are asked about two scenarios of the same object, right? Since we are asked about two scenarios of the same object, when we are going to apply the same equation twice or more than that, right? Always we can cancel the constant terms and divide equations. That will be easy. No need to deal with constant terms. I'm going to cancel this. See, k is constant, m is constant, same object, 4 5 squared is constant. So therefore, from this equation, this is the only part that I need for the proceedings. X proportional to, if constants are cancelled, then proportionate signs remain. Proportionate signs remains. R over T squared. Right? Now I'm going to use this equation twice. See, for the first one, extension is R. Extension is R. And radius of rotation is 2R. Radius of rotation is 2R. Period is T squared. And for the second scenario, since radius is 3R, extension is 2R. Extension is always the additional length compared to natural length. Additional length extended or elongated compared to natural length. So it's given as the unstretched length of the elastic string is R. No, unstretched length is the natural length. Right? So extension is the expanded length, and the additional length beyond the natural length, right? So there is 2R here, proportional to 3R over. So let's say this is t dash squared. Now divide these two equations. When equations are divided, again proportionate signs becomes equal signs, right? So R to R cancels. R to R cancels. Now we can divide the equation from left hand side 1 over 2 equals from right hand side 2 over t squared. Multiplication with the reciprocal 3 over t dash squared. I need t dash. So subject t dash squared. T dash squared is 3t squared over 4. So t dash is root 3t over 2. T dash is root 3t over 2. Root 3t over 2. Root 3t over 2. Answer is answer 4. For 7, answer is 4. For 7, answer 4. Can you explain again? Okay, listen again. So, if you don't know Hooke's law, first thing, this is called Hooke's law. F equals represents force, K is elastic constant or spring constant, and X is extension. Extension is the length beyond the natural or unstretched length. Right? Now, when this car undergoes in a circular motion, we can use F equals ma towards center. No? Right? We can use F equals ma towards center. Now, since this is a string connected, on this string there is a stretch string. No, this force exerts, and this car undergoes in a circular motion like this. So when we use F equals ma towards center, only force which acts towards center is F. So F can be expanded as kx. This is the force on the elastic string. Force on the elastic string. So we call that as the tension on elastic string. Both are fine. Tension on elastic string or force on elastic string. Right? Then A can be expanded as R omega squared, M R omega squared. Omega is 2 pi over D. Expand it. And then since we are applying the equation 2 times, same equation 2 times, cancel the constants. Then we have this equation. Apply the equation 2 times. Divide it. And subject T dash. Right? So we have T dash as root 3 over root 3t over 2. Answer is 4. Write it down quickly. You can take it down. Okay, let's move on. Question 8. Question 8. Question 8. Two small objects of equal masses are attached to each other by a light string BC, and the system is connected to a fixed point A, which with another light string AB as shown in figure. Okay. Now we have to have a good idea about this diagram given. See, first we have to get this idea. The mass is here, and this is a second string A B C. A B C. Okay. Two small objects of equal masses. Equal masses, no? So let's consider they are M and M. They as M and M. With another light string AB as shown in the figure, the masses are then made to move in horizontal circular paths of radii R and 2R. Right? So radii R and 2R. This is R and this radius is 2R. Right? Total, total is 2R. Otherwise, only this part is R. Total is 2R. With the same angular speed, so that points A, B, and C are always in a straight line. Points A, B, and C are always in a straight line. If T1 and T2 are the tensions of strings BC and AB respective, then okay. Now that's a circular motion, no? Fine. Now if you understood this diagram, hereafter the question is very simple. That's a circular motion. If there is a circular motion, we can use F equals MA towards center for both masses individually, yeah, separately. Tensions are marked T2 and T1. So this tension is marked as T2. This one T2. And this is T1. This is also T1. This is T2. Right. Now, for simple M here, see, look at here. F equals MA towards center. F equals MA towards center. F equals MA towards center. For first one, if we apply F equals MA towards center, what we get is T2 minus T1 equals T2 minus T1. Let me write it here. F is T2 minus T1 equals M. A can be written as R omega squared. So M R omega squared. Because A equals R omega squared. Right? So I will consider this as equation 1. And then for next one, again we can use F equals MA towards center. And only F for the other object is T1. Right? So this is for B. For your clarity, this is for B. Yeah? This is for B. And this is for C. This is for C. Only force acting towards center of C is T1. Can be written as same M, but radius is 2R, omega is same, 2R omega square. Right? I'll consider this as 2. Now, what they ask is a relationship between T2 and T1. No? That is actually T2 in terms of T1. That is actually T2 in terms of T1, which means there is a relationship between T1 and T2. Right? If you can divide the equations, you can divide the equations and get the answer, because I need to cancel MR omega square. Or else we can substitute. I'm going to substitute because here we have an answer for MR omega square. No? From 2, I can write, see, from 2, I can write T1 equals 2 times MR omega square. 2 times MR omega square. Right? So therefore T equals 2 times MR omega squared can be written as T2 minus T1. Right? MR omega squared can be written as T2 minus T1. Simplify this. T1 equals 2T2 minus 2T1. Take it to the other side. 3T1 equals 2T2. Subject T2. T2 is 3T1 over 2. 3T1 over 2. Right? Very simple. 3T1 over 2. T2 is 3T1 over 2, which means answer 4. For 8, answer 4. Write it down. Right? You can ask questions if there's anything. You can ask questions if there's anything. So otherwise, I assume that you have no questions and I'm moving on. Right? Next one. We are moving on. Next one. Nine. A sphere capital M attached to a thread is whirled in a horizontal circle at a constant speed as shown in the figure. The forces acting on the sphere observed by a person who is at rest in the laboratory are best represented by. Right. So again, a similar type of question to what we discussed before, and before I ask question 4-5. Yeah. Before I ask question 4-5, a similar type of a question. Now from these force frames, that is called force frames, from force frames and relative motion, very popularly questions are coming in circular motion. Right. So look at here, question 9. Right. So if it undergoes a circular motion, now check what forces act here. Mg acts. And since there's a string here, tension acts. Right. Now similar to the previous one. Right. Now the circle is this, no? Horizontal circle is this. So center of the circle is somewhere here. So therefore, see, one component of T, let's say T cos theta, one component of T acts as centripetal force here. One component of T acts as centripetal force here, and the other component counterbalances mg. Right? So therefore, what a person from outside see is, what a person from outside can see is only tension and mg. Only tension and mg. And in the last question also, I explained that for the persons for a force frame who is outside the circular motion cannot feel centripetal force. Right? So therefore, there is only tension and mg. Answer is true. Answer is true. Only the tension and mg can be seen. Only the tension and mg can be seen. Answer is true. Answer is true. Only the tension and mg can be seen. Right? Write it down quickly. You can take it down quickly. Right, moving on. Question 10. Question 10 is a very good question. Very good question, which has a uh, combination, a twist with vectors. Right? Which has a combination, a little bit twist with vectors. Right? A particle is moving in a circle with constant speed v as shown in the figure. The magnitude of the change in velocity of the particle between points p and q is. Right? So that is never going to be zero because that's a change of velocity. Even if the direction changes, velocity changes. Right? If that was change of speed, that is zero. If that was change of speed, that is zero. Now that is change of velocity. Even if the direction changes, velocity changes. So that is non-zero. That is non-zero. Right? So look at here. These are the 2 points given with an angle 40. So we know always velocity is tangential. Velocity is tangential. In a circular motion, velocity is tangential. Right? So therefore, this velocity acts in this direction and it makes an angle 90 here, tangential. And this velocity acts towards this direction and it makes an angle 90 here. Right? Now, basically, there are two methods of doing this question. Right? I'll show you both. I'll show you both. So first I'm going to simplify these two as two vectors. Simplify these two as two vectors, right? So for that, I'm going to identify these angles. Look at here. I can extend this backwards now. If I extend this backwards, so I can see something like this, right? If I extend this backwards, and to identify these angles, I'm going to create these vertical lines. I'm going to create these vertical lines. My purpose is to identify angles. And I can create this bisector as well. I can create the bisector as well. Right? Now, we can identify these angles. If there is a bisector, this is 20. Very important, this is 20. If there is 20, right, this is 90. So this becomes 70. If this is 70, right, and this angle is again 20. If there is 20, this angle becomes 20. So one angle is identified, this is 20. And similarly, if this is 20, this is also 20 now. If there is 20, this angle is 70, 70. So this is 20. Then again, this becomes 70 and this becomes 20. And here it will be 20 again. Sorry, not there. Here, here, here. Here. 20, 90, 70, and this is 20. This is 20. 20. Right? Now I have two vectors. I'm going to simplify these two vectors using a vector triangle. Using a vector triangle. Now we need what we need? The change of velocity, delta v. Look at here, delta v, change of velocity is final minus initial. No? So final velocity is this. So direction of final velocity is v with angle 20 minus initial velocity is another v with this angle 20. Right? Now we can rewrite the same thing as if the sign in front of a vector changes, its direction changes. If the sign changes, direction changes. Now this can be written as a vector in this direction v in this same angle with this same angle. Right? Now I'm going to represent these two using a vector triangle. I'm going to represent these two using a vector triangle. So this is v with 20, and this can be connected to this point as it is 20 as it makes 20 like this. So this is the vector triangle, and this third side of the vector triangle from here to here gives us the resultant. So it gives us the resultant. Let's say R. It gives us resultant. Right? Now very straightforward. If this is V, now this is right angle. No? So if this is V, this can be written as V sine 20. And this can be written as, this is also V sine 20. This is also V sine 20. So therefore, R equals 2V sine 20. Therefore, R equals 2V sine 20. 2V sine 20 answer is there, answer 3. 10, answer 3. Two V sine 20. This is a very good question as a combination of circular motion with vectors. Vectors, actually, I'm using the vector triangle here. Vector triangle, a usage of a use case, an application of vector triangle. Take it down. This is method 1. I'll explain two methods of doing this. This is method 1. This is method 1. I'll explain another method to do the same. This is method 1. Is it clear enough? Students, is it clear enough? See how these things we learned in mechanics links to each other. Now this is coming from vector triangles, vector triangle, right? So that is linked with the circular motion application here. Right? A good question, very good question. With a good thinking. Some of you might be thinking that as zero, no? Because if a direction changes of velocity, definitely there's a change. There's a non-zero change for that vector. Okay. Is it clear? Is it clear enough, students? Yes, right. So there's another method to do this. I'll explain the method 2 as well. There's another method. To it here. It's a good question, no? Method 2. Method 2 is now if we are determining a change of a vector, right? Simply, we can consider now if they are inclined vectors, huh? If you are determining a change of a vector uh, or two vectors of in inclined directions, right? What we can do is we can take the change in perpendicular directions and get the resultant, get the net one, right? So therefore, first I'm going to determine the change in vertical direction. Method 2 is see, vertical delta V. Vertical delta V is final vertical component is V cos 20. V cos 20 minus initial component is also V cos 20. So therefore, vertical change is 0. Then horizontal change. Then horizontal change. Horizontal delta V to get here equals final component is V sin 20. No? Acts along this V sin 20. V sin 20 minus and this component acts towards this. That is also V sin 20, but that is opposite. That is opposite. So therefore, that is minus V sin 20. So minus V sin 20. Minus V sin 20. Simplify this. That is 2V sin 20. 2V sin 20. The final resultant is going to be this because there is no change of velocity in vertical direction. So final delta V is 2V sin 20. So therefore, delta V is 2V sin 20. Therefore, delta V is 2V sin 20. Right? So this is also a possible method. You can get used to anything you prefer. And you have to know both. That's most important thing is that you have to know both because from question to question, right? The easier approach changes, right? It changes from question to question. So therefore, we have to decide that at the question, right? Based on that context of the question, we have to decide it, right? That's the thing. That's the thing. So therefore, you have to know both. Take it down as method 2, right? So we are moving on. So this is a very good question. The one we discussed now. This one was a very good combination with vectors, right? A nice combination with vectors. 11. 11. A particle is moving in a circular orbit of radius 10 meters. At one instant, the speed of the particle is 10 ms minus 1. Right? A particle is moving in an orbit of radius 10 meters. Right? So at one instance, the speed is 10 ms minus 1. And increasing at a rate of 10 ms minus 2. So that is actually about the acceleration. No? 10 ms minus 2 is the acceleration. So in the same direction, we have an acceleration of 10 ms minus 2. The angle between the velocity vector and the resultant acceleration vector of the particle at that instant is resultant acceleration vector. Now, velocity vector is known, that can be seen easily. Velocity vector is this. Now, then we need to find out where the resultant acceleration vector is, right? So we know that there are two accelerations act on, an object which undergoes in a circular motion, right? These two are called tangential acceleration and centripetal acceleration, right? Look at the here. Look at the board here. Look at the board here. So I'll explain this first. Now, if this is an object which undergoes a circular motion like this, right? There are two acceleration components as one along the tangent, that is called AT, tangential acceleration, and there is another acceleration component that is along, that is towards the center, along the direction of center, that is called centripetal acceleration. So therefore, resultant acceleration of a circular motion is the resultant of these two. Resultant acceleration of a circular motion is resultant of these two. Now I'm going to decide these two. Right? Centripetal acceleration can be written as, look at here, that is towards center, centripetal acceleration, AC. AC can be written as, now we have been discussing the equation from the very beginning. AC can be written as either V squared dou R or R omega squared. So therefore, AC equals V squared dou R. V is 10. So 10 times 10 over R is also 10. These two cancels. Centripetal acceleration is 10 ms minus 2. Right? And tangential acceleration is given. That is also 10. That is also 10. Right? So therefore, the resultant of these two, they are two vectors of 10 and 10. No? So they act in between. The resultant of these two acts in between. And since vectors are same, angle will be equally divided. 45. Very easy. Very easy. Now these two vectors are same. Right? 10 ms minus 2 AC. And here AT is also 10 ms minus 2. So the resultant is in between. Right? So if you really need to determine this angle, we can write tan theta and determine it. But no need, because if forces are same, the resultant is exactly in between. Right? So therefore, this is 45. So if this is 45, this is also 45. Right? Now, the question is the angle between the velocity vector and the resultant acceleration. Velocity vector is this, resultant acceleration is this. So angle in between is 45. Angle in between is 45. So therefore, angle in between is 45. So final answer is 45. Angle in between is 45. This is the angle. 45. A good question. Good question. Take it down. So from the theories, what you have learned in circular motion, now you can see what's the extent we can go in circular motion. It can be connected to anything. Take it down. Sorry. Right, finished? Yeah, moving on. Hope it's clear. Can you give me a quick confirmation? Is it clear? Students, is it clear enough? Can you give me a quick confirmation, a quick response? Is it clear enough? Students, is it clear now? Okay, if there's no questions in the chat, so I assume it as clear, right? I'm going to move on. I assume it as clear, right? Okay, next. It was question 11, right? 11 answer is 345. For 11 answer 345. 11 answer 3. Next one. 12. Figure shows a space colony of radius 10 to the power 3 meters, rotating about this axis. At what angular speed omega must the space colony be rotated so that the astronaut standing in the flow of the colony experiences a push on his feet that equals his weight on Earth? That equals to his weight on Earth, right? Look here. That astronaut is here. Astronaut is here. And this radius is given. Radius is given as 10 to the power 3 meters. So this rotates. Now this astronaut also, he also uh, undergoes in a circular motion, right? Because when this space colony rotates, the astronaut also undergoes in the circular motion, right? And there will be a perpendicular reaction on that person like this, on an astronaut like this, right? A perpendicular reaction. And the direction of that reaction is exactly towards center. Direction of that reaction is towards center, right? So therefore, we can use F equals ma towards center, right? Now, in a circular motion, so there are very straightforward things to do. Applying F equals ma towards center. If there is a horizontal circular motion, we have to consider vertical equilibrium. If there is a vertical circle, we have to consider conservation of energy. So likewise, things we do are very straightforward. Right? So here also, again, I'm going to use F equals ma towards center. Look at the board. Towards center. Towards center, F equals ma. So only force is R, and omega is asked. So M R omega squared. And they say that R equals mg because the hint is they say that the reaction to push his feet with a reaction that equals his weight on earth. His weight on earth is mg. So therefore, this is mg. mg equals m r 10 to the power 3 omega squared. M to m cancels. Right? M to m cancels. G is 10 no? So simplify this. 10 equals 10 to the power 3 omega squared. Then 10 to this cancels 10 to the power 2. Omega squared equals 10 to the power minus 2. Omega squared equals 10 to the power minus 2 means omega equals 10 to the power minus 1. Right? So which means 10 to the power minus 1 is 0.1. Unit of omega is radians per second. So answer 1 for question 12. Take it down. Answer 1. That is easy, comparatively easy. Comparatively easy. Just an application of F equals ma towards center. Right? Just an application of F equals ma towards center. Take it down. For 12, answer 1. Answer 1. Okay, next 13. 13. It says a small object of mass m is suspended by a string of length L and is allowed to move in a horizontal circular path about the vertical axis passing through O. As shown in the figure, if the air resistance is negligible, the velocity of the particle is right. Okay. Half vertex angle is given. See, this motion of the bob is called a conical pendulum. So in physics, this motion of the bob is called the conical pendulum. This is L, and this angle is given as theta. Right. So mark forces acting here. Weight mgx vertically downwards, and tension on this string. Tension on this string. Right. Okay. Now to consider vertical equilibrium and apply F equals ma towards center, I need to dissolve this. I need to dissolve this. Right. So the component acts towards center from this is, now if I extend this vertical line, we can see this is theta, this is also theta. Alternating angles, right? From here to here. Alternating angles. Right. So therefore, this component is T cos theta. T cos theta. And this component is T sin theta. This component is T sin theta. Right? Now, what we can do is first thing vertical equilibrium. See, this is vertical equilibrium of simple M. Vertically upwards forces equals vertically downward forces. Vertically upwards we have T cos theta. T cos theta. Vertically downwards mg. So I consider that as equation 1. T cos theta equals mg. Right? And then we can use F equals ma towards center. Towards center. Towards center direction now is this F equals ma. Only force acting towards center is T sin theta. Only force acting towards center is T sin theta. Right? And they are asking about the velocity. About the velocity. So expand it in terms of velocity. Expand it in terms of velocity. So that can be expanded as mv squared over r. R is L. Because A equals v squared dou r. Because A equals v squared dou r. R equals L. Right? So now I consider this as equation 2. Right? Tension should be cancelled. Tension should be cancelled. So therefore, I'm going to divide these two equations. Right? To create tan 2 over 1. 2 over 1. Then this is T sin theta over T cos theta. T sin theta over T cos theta. And here we have mv squared over L. And this is divided by mg, which means multiplication with reciprocal 1 over mg. Right? Look at here, m to m cancels. T to T cancels. So everybody know that sine over cos is tan. So this can be written as tan theta. Tan theta equals from this side I have v squared over gl. Subject v squared, because my target is v. Subject v squared equals gl tan theta. So v equals root gl tan theta. V equals root gl tan theta. GL tan theta, it is given as LG tan theta root. Answer is 3. For 13, answer 3. For 13, answer 3. Right? Take it down. And ask questions if you have anything. This is called the conical pendulum. Conical pendulum. Okay, next. Let's move on. No questions, no? So you can always forward your questions if you have anything. You can always forward your questions if you have anything, right? And the questions are uh, mostly welcome, right? Question 14. We are moving on. Question 14. 14. A car of mass M monetizes a circular bend of radius of curvature R in a horizontal road with a speed V. If the car skids, then mu is the coefficient of friction between the road and tire. An inequality given. An inequality given. Right. Okay. Now look at here. Horizontal bend. No. That's a horizontal bend. Now the car travels like this. Car travels like this. Right. Once the car travels, we know that if it undergoes in a circular motion, right, there's a centrifugal force exerts due to circular motion. To counterbalance that centrifugal force, right, to counterbalance the centrifugal force, centripetal force acts. And here friction acts as centripetal force. Here friction acts as centripetal force. Right? So therefore, in this direction towards center, we have friction. And away from center, we have centripetal force. Centripetal force can be written as mv squared dou r. Right? This is centrifugal. This is centripetal. This side centripetal, and this is centrifugal. If these two forces are equal, it undergoes a perfect circle. Right? If these two forces are equal, it undergoes a perfect circle. Now, if it skids, right? It's given as skids. No, if it skids, which means that is due to higher velocity. That is due to higher velocity, right? That is due to that exceeds the maximum velocity. So therefore, it skids if this centrifugal force is greater than the friction here, because friction cannot be adjusted. Friction is mu r, mu remains same, r remains same. So at one point, if centrifugal force exceeds the friction force, then it skids. Now, otherwise, friction is never going to exceed centrifugal force because friction is a constant value, right? Friction is a constant value. So therefore, what happens is if centrifugal force exceeds friction, friction can't counterbalance that force. So it skids. So therefore, this is the argument I'm going to have. If skids, look at here, if skids, if skids, the reason is centrifugal force is greater than friction. Centrifugal force is greater than friction. Okay, now simplify this. mv squared over r greater than f can be written as mu r because f equals mu r. And let me mark these forces here. Reaction x, other than that mgx, right? But from here we know r equals mg. R equals mg. Vertical equilibrium, r equals mg, right? So here also I will mention that r equals mg. You can plug that. mv squared over r greater than mu mg. M to M cancels. What is subjected? V is subjected. So V squared is greater than mu gr. So V should be greater than root mu gr. V should be greater than root mu gr. V should be greater than root mu gr. It's given as root mu rg. Answer 1. For 14, answer 1. For 14, answer 1. Take it down. 14, 1. For 14, that is answer 1. Write down. Right. Hope it's clear. So if you have any questions, you can quickly ask. You can put anything into the chat box. Okay, no questions now. We are moving on. Question 15. Question 15. Question 15. The athletes run a 10-kilometer race with constant speeds V1 and V2 in a circular track of radius 50 meters. Circular track of radius 50 meters. It has been observed that the athlete with speed V1 complete 10 rounds when the other athlete complete 9 rounds. The ratio V1 to V2 is. Okay. Another good calculation. Look at here. Look at here. Here we have two athletes. Look at here. Two athletes. Track of radius 50 meters. Track of radius 50 meters. And one athlete runs with a speed V1 and the other runs with a speed V2 and the other runs with a speed V2. A very important data is given that times taken to complete 10 rounds and 9 rounds by both are equal, right? Times are equal now. So I'm going to start from that point, right? I'm going to start from that point and yeah, finally we need the ratio between V1 V2, right? Okay. So my target is this. Listen first. My target is this. By considering this given time data, I'm going to connect it with periodic time. And then if I have connected it with periodic time, then I can connect it with omega. If omega is known, which means V is known. So we can go that way, right? See, so we can say these times are equal now. T1 equals T2. T1 equals T2. There is a given data. Times are equal. Periodic time is time taken for a complete cycle. Periodic time means the time taken for a complete cycle, right? Now, if the first one completes 10 rounds, right? So let's assume its periodic time as T1, then that should be 10 T1. No? This T1 should be 10 T1. 10 T1. Because periodic time is the time taken for a complete cycle. If 10 cycles, then 10 times periodic time. For the other one, let's assume its periodic time as T2, 9 T2. Right? And now we know this relationship. Omega equals 2 phi over T, which means T equals 2 phi over omega. T equals 2 phi over omega. Right? So expand this 10 times. T1 can be expanded as 2 phi over omega 1. And 9 times T2 can be expanded as 2 phi over omega 2. 2 phi to 2 phi cancels. Right? And now again we have a relationship like this. I'm going to cross multiply 10 omega 2 equals 9 omega 1. I have been asked about the relationship between a ratio between V1 and V2. So if we know omega, easily we can convert it to V. Relationship is omega is V over R. Omega is V over R. Omega is V over R. Then 10 omega 2 will be V2 over R. R is 50. And 9 times omega 1 is V1 over R. R is 50. Right? So 50 to 50 cancels. Create V1 over V2. Create V1 over V2 from this ratio. V1 over V2 is 10 over 9. If you understood the question, this is a very simple and easy calculation. A simple and easy calculation if you get the question properly. 10 over 9, answer 1. 15, 1. 15, answer 1. Write down. Write down. Right. So we are moving on. Moving on. Question 16. That's a statement question. 16. One end of one end each of two identical stretched springs are fixed to two ends of a closed tube, and the other ends of the springs are attached to a mass M. Okay. So let me take down the diagram. Now this is inside the tube. This setup is inside the tube, and here we have one spring. Mass is in between, and the second string is here. Spring. Second spring is here. Right? P and Q. Ends are P and Q. P and Q. This is simple M. Simple M. Right? Which of the following mentions of the system results in a displacement of mass M towards P from the center of the tube? Right? Displacement towards P. Okay. Let's check one by one. First one. Uniform acceleration of tube in the direction of PQ, keeping the tube horizontal. Okay. Check first one. This is going to be accelerated in this direction. This is going to be accelerated in this direction. Right? Now, when it comes to a spring also, Hooke's law is valid. I explained Hooke's law in one of the previous questions. Right? For a spring also, Hooke's law is valid. Hooke's law is F equals Kx. So let's assume forces which exerts on these springs as let's assume them as T1 and T2. This one, let's say T1, and for this one, let's say T2. These are the forces exerts on the springs. Now, if I use F equals ma for simple M and C, for simple M, leftwards F equals ma. T1 minus T2 equals ma. T1 minus T2 equals ma. Right? So that's a positive value. T1 minus T2 equals ma, and if needed, T1 can be expanded. T1 can be expanded as Kx1. Right? Okay, K1, X1. Are they identical? They are identical. Then K is also same. K is also same. Then Kx1 minus Kx2. Now, without going to that depth, now this is a positive value. Since there is a positive value, T1 is greater. Right? So definitely T1 is greater. T1 is greater than T2. Since T1 is greater, right, the tendency of motion on M is towards P. Since T1 is greater, tendency of motion of M is towards P. Right? So therefore, I can decide that here that M moves towards, M tends to move towards P. M tends to move towards P. M tends to move towards P. Right? So A is correct. Second one, rotation of the tube around the vertical axis, passing through Q, keeping the tube in a horizontal plane. Right. So if it rotates around this, now what happens is, that is very straightforward. If there is a rotational motion, if there's a rotation for this simple length, that will be a circular motion. Right? For simple length, there is a circular motion. So if simple length undergoes a circular motion, which means centrifugal force exerts on simple length. So we know that always if something undergoes in a circular motion, the motion is always away from center. Right? Motion is away from center. Moving tendency is away from center due to centrifugal force. Right? So therefore, now if this is going to be the point of rotation, away from center direction is this. Right? So centrifugal force acts. Centrifugal force acts. So that causes a movement of M away from center, which means towards P. So B is also correct. Now from this, A is correct. Right? So due to the centrifugal force, B is correct. Right? Let's check C. Vertical motion of the tube under gravity, keeping Q below P. Something like this. Vertical motion under gravity, keeping Q below P. Right? Now, these tensions are, look at here. Now, these tensions are, let's say T1 and T2. Right? So, Mg also acts. Now, if we apply F equals Ma here, downwards, F equals Ma, right? Mg plus T2 minus T1 equals Ma. A is also G, because that is moving under gravity. If anything falls under gravity, it falls under gravitational acceleration. Right? If anything falls under gravity, it falls under gravitational acceleration. So that is G. Right? Simplify this. Mg plus T2 minus T1 equals Mg. These two cancels. So it gives T2 equals T1. If T2 equals T1, there is no any moving tendency of this object towards either of the sides. If T1 equals T2, no motion towards either of the sides, because T1 and T2 will be balanced. That is counterbalance. Right? So therefore, no motion. No motion means it is not moving towards P. Right? So no motion. Not moving towards either side. So therefore, C is wrong. Only A and B are correct. Only A and B. That is in answer 2. For 16, that is 2. So this is a very good statement question from circular motion. That is actually a combination of circular motion with Hooke's law. Hooke's law is something coming up in oscillations and waves, unit 3. Can you explain how A and B are correct again? Okay. First one, about A. Now, if we try applying F equals Ma towards this direction, since acceleration is positive, this is a positive value. Right hand side of the equation is positive. If we think mathematically, right hand side of the equation is positive. So therefore, left hand side is also positive. It should be positive. Therefore, in order to be this positive, T1 is greater than T2. If T1 is greater, the tendency of motion on M is towards P. Tendency of motion on M is towards P. Right? Because T1 is greater. That is towards P. So therefore, M tends to move towards P. That is correct. They are asking about the motion towards P, no? Right? And about B, if it rotates around, simple M undergoes a circular motion. If there is a circular motion, centrifugal force is exerted on the object. So direction of centrifugal force is away from center. So this is the direction of centrifugal force. So with that centrifugal force, M also moving towards away from center. M moves towards away from center. When it moves away from center, it's moving towards P. So that is also correct, right? So there is no moving tendency here towards either of the sides, or A and B. So therefore, there is no motion, not moving. That is incorrect. So only A and B are correct, right? Hope it's clear. Hope it's clear. Okay, take it down. This is a very good question. Very good question. There we have three good arguments. Three good arguments. Three good arguments. Right? Time is enough. Enough, no? Right. We are moving on. So now it was question 16. Only A and B. Answer is 2. Right? Next. 17. So in 17th and also there is an application of spring. So if there is a spring, it follows Hooke's law. Hooke's law is F equals Kx. A light spiral spring has an unstretched length L and a spring constant K. A small object of mass simple m is attached to one end of the spring and the system is rotated about a vertical axis that passes through a small light ring attached to the other end of the spring as shown in the figure. If the object travels along a circular path of radius capital R with constant angular speed omega, keeping the spring on a horizontal plane, then omega. They are asking omega. Omega. Okay. To get here. So first, understand how this the force frame works. How this force frame works. Right. This is given as R, and this is M with omega. Right. Now, if there's a stretched spring, if a spring is stretched, right? If a spring is stretched, what happens is there's a force exerts on the spring, right? If any spring is stretched, a force exerts. If a spring is compressed, also there's a force exerts. Now this is stretched, no? So there's a force exerts in the spring. That is very similar to a tension. That is very similar to a tension. If there is a stretched, that is similar to a tension. If there is compressed, that is similar to a thrust force. Now this is F. This is the force on the spring. Since it is a circular motion, right, very straightforward. We can use F equals ma towards center. We can use F equals ma towards center. See? Towards center. towards center, F equals MA. F is this F. M, A can be written as R omega squared, right? But we know from Hooke's laws, F equals Kx. F equals Kx. I explained the Hooke's law in previous two of the questions as well. F is force on the spring, K is spring constant, X is extension, right? So F is Kx. That is mr omega squared. X is extension, no? Extension is the stretched length beyond natural length or unstretched length. Now it is given as unstretched length is L. If unstretched length is L and if the radius now is R, the stretched length is R minus L. Right? Stretched length is R minus L. So this can be written as K times R minus L equals mr omega square. Right? Omega is subjected. Omega. Okay. Then omega squared can be written as K times R minus L over mr. K times R minus L over LR. So subject omega. Omega is the square root of K times R minus L over mr. So that is given in answer 1. K times R minus L over mr. Answer 1 for 17. Answer 1. For 17, answer 1. Right? Write it down. Write it down. How did you get R minus L? R minus L. Because X is the extension. X is extension. In F equals Kx, X is extension. Right? Extension is the extended length beyond unstretched length or extended length or stretched length beyond natural length. In the question, it is given as natural length or unstretched length of the spring is length L. Unstretched length of the spring is L. Now, something like this. Unstretched length of this spring is L. Right? Now, in this scenario, there is a stretch. Now, in this scenario, there is stretch to a length R. That is stretch to R. So, this part is the extension. This part is the extension. This is the extension. So, this is X. So, it can be written as R minus L. It can be written as R minus L. Can be written as R minus L. Now, it's clear, right? Take it down quickly. So if you have anything you didn't get about these questions, you can always question me and clarify it, right? So if you have anything that you didn't get, you can always question me. So we are in last three questions now. We are in last three questions, right? Okay, let's move on. 18. 18. 18. An object is moving in a circular path at a constant speed v as shown in the figure. The change in velocity of object when moving from A to B is. Can you remember we did the same question before? We did the very comparative similar question before. It was question 10. So question 10 is very comparative. That was at year 2005, right? And in again 2019, can you see the same question has appeared? Same question has appeared. So that's the advantage of doing more past papers. That is the advantage of doing more past papers because even though the exact same question is not coming, right? Always similar types, very comparative, similar questions are always coming, right? So therefore, that's the advantage. That's the benefit, the exact benefit that you can have if you do more past paper questions, right? Now, if someone has done the 2005 question, definitely that student will tackle this 2019 question for sure, because this 19 one is with the right angle. That is very easy compared to that angle with the angle of 40 in 2005. So when we have 40, we have to do like we have to put much effort or more effort to find out other angles. But when a 90 angle is given, that is very much straightforward. No dissolve components also, right? So that's the advantage. So keep that in mind. Always try to do more past papers. The more you do past papers, the more you gain the knowledge and the more you are familiar with the lesson. So which means once another similar question, similar type of a question appears, you would tackle the question easily, right? So that's the advantage, and that's actually the purpose of doing past papers to get that experience, right? 18 from A to B. Look at here. O angle is 90 at A and B. So we know velocities are tangential. Always velocities of a circular motion are tangential. So this velocity here is along this tangent. This is here along this tangent, right? So these are perpendicular with the normal drawn to the center, right? We need the change in velocity now. So directly apply change of velocity. Now for this one also, the both methods I explained in the question 10 are valid. Either you can use a vector triangle or else you can just write the change and get it done, right? So I'm going to use a vector triangle. See, delta v, final minus initial, no? Final velocity is v upwards minus initial velocity is v rightwards. V upwards minus v rightwards. Right? If we need to change the sign of a vector, the direction of vector changes. If we need to change the side of a vector, direction of the vector changes. So this can be written as plus this. Now easily I can determine this using the triangle. See, vector triangle. If I apply these two in the vector triangle, this is a vector v and this is another upward vector v. So resultant gives this 90, no? Angle is 90. So resultant vector is the vector from start to the end. That is the vector from start to the end. That is the resultant vector, right? The value is also asked if vectors are equal, if perpendicular vectors are equal. So I have discussed these things in the class, right? If perpendicular vectors are equal, resultant is always root 2 times one vector. Resultant is always root 2 times one vector, right? So since this is an isosceles right angle triangle, this angle is 45. Angle is 45. If you need to determine resultant, now since this is MCQ, listen, since this is MCQ, now you have to know these things. If you know these things, you can easily pick the answer. You can easily pick the answer. So remember this point onward, if we have two equal vectors, two identical vectors in perpendicular set up like this, in a perpendicular like this. So simply, if you have two equal perpendicular vectors, resultant is always root 2 times one vector. Resultant is always root 2 times one vector, right? See, I'll prove it here. Now R can be written as square root of v squared plus v squared, no? Right? So that is 2v squared square root, that is root 2v. So R equals root 2V. R equals root 2V. And the direction is this 45 angle. Answer is 4. Answer is 4. So 18, 4. Take it down. Take it down. Right? So very similar to question 10. And this is actually easier than question 10. This is much easier compared to question 10. And question 19. 19 is another very good calculation we have here. Question 19 is a very good calculation with friction. Right? That is one of the good questions appeared in recent past, 2019. Right? Okay, let's move on. Move on. Let's move on. Question 19. So moving on to question 19. So last two questions. We are in last two questions. A small object is placed inside a right circular cone with axis vertical and vertex down, as shown in the figure. Axis vertical and vertex down. Right. So it's clearly given in the diagram. It's clearly given in the diagram, axis vertical and the vertex down. Something like this. Axis vertical and the vertex down. Right. The coefficient of static friction between the inner surface of the cone and the object is mu. Right. So object is given here. That is given here. The distance is given as d. What is the maximum angular velocity of rotation of the cone about its axis for the object to be on the inner surface of the cone without slipping at a distance d away from axis? At a distance d away. Okay. Now, if there is staying without slipping, which means there is a perfect circular motion. We call that a proper circular motion. So if there is a proper circular motion, so we can do the things that we do for a normal horizontal circle and see whether it's coming. So what they're asking is maximum angular velocity. Maximum angular velocity. We need omega. We need omega. Right? So first mark these forces. mgx. Vertically downwards mgx. And perpendicular to the surface, reaction x. Perpendicular to the surface, reaction x. And higher the speed, higher the velocity, or higher the angular velocity, always due to the impact of centrifugal force, the object tends to move away from center. Object tends to move away from center. So therefore, what happens is friction will be inward the surface like this. So this is friction. Right? Downward the surface, inward to the vertex. And this angle is given, right? Theta. Angle is given, theta. Okay. Now, I'm going to extend this vertical line and check these angles because I need the angles for my dissolved components. If this is theta, this is 90. 90 minus theta, this angle becomes theta. If that angle is theta, and if this is 90 minus theta, this is again theta. So likewise, you can determine where the theta is. You can determine where the theta is. Right? Now, we are doing the normal two usual things we do for a circular motion, for a horizontal circular motion. First thing, vertical equilibrium. See, using vertical equilibrium, using vertical equilibrium. vertically upward forces equals vertical downward forces. Vertically upwards I have r sine theta. R sine theta. Only r sine theta. Vertical downwards we have two forces, F cos theta plus mg. But we know F equals mu r. But we know F equals mu r. Mu is given. So expand it. Expand it. R sine theta equals F is mu r cos theta plus mg. R is common, no? So I'm going to take this to the other side and take r out. Right? This is r sine theta minus mu r cos theta equals mg. So if r is taken out, sine theta minus mu cos theta equals mg. I'll keep this as equation 1. I will keep this as equation 1. Right? Then the only thing left to do is applying F equals ma towards center. So apply F equals ma towards center. Apply F equals ma towards center. See? So be mindful with the simplification. Here there are more terms involved in the simplification. This is towards center. Towards center. Towards center direction is this. F equals ma. F towards center is, we have one component of r, that is r cos theta. We have another component from friction, that is F sin theta. No components from mg, because mg is perpendicular to the considered direction. If there is perpendicular vectors are neglected. Perpendicular vectors are neglected. And we need omega, no? So expand this as m r omega squared, because A equals r omega squared. A equals r omega squared. M r omega squared, r is d now. md omega squared. Right? Okay, again, we can expand these terms. F equals mu r, no? R cos theta plus mu r sin theta equals md omega squared. Take r out. Cos theta plus mu sin theta equals md omega square. Now for r, I have a substitution from this, no? For r, I can use the substitution from here, right? Now look at here. After this, now I'm going to take this calculation to here and going to plug r. R can be written from here as mg over this thing, mg over this part. R is mg over this part, no? So going to substitute. Be careful. R is mg over this part, sin theta minus mu cos theta, times here I have sin theta. Sorry, here I have cos theta, times here I have the remaining part cos theta plus mu sin theta equals md omega square. Right? So hope the substitution is clear. Now m to m cancels. Right? A good question. Subject omega squared. Cross multiplication. Omega squared equals, we can cross multiply this, d to the other side. Then here g times cos theta plus mu sin theta over g times this over, from here d comes, d times sin theta minus mu cos theta. This is omega squared. We need omega, so take the square root. So omega is square root of this whole thing, g times cos theta plus mu sin theta over d times sin theta minus mu cos theta. Final answer. Right? A very good calculation, and this was actually the longest calculation we had in all questions, right? The longest, and with the highest number of terms. So what's the answer? G cos theta plus mu sin theta over d sin theta minus mu cos theta. Answer is 3. 19, 3. So 19, answer 3. Take it down. This is a good question, a very good question. And if you have anything to clarify, if you didn't get, if you have anything that you didn't get from the question, you can always question me and clarify it. Right? You can always question me and clarify it. Since this was a very good question, uh, now if it is clear enough, say it's clear enough, then I know that you have got the answer and you are on the track. Then I have an indication that you are on the track now. Right? So say it's clear if that is clear. How did you mark the friction? Because always moving tendency of a circular motion is away from center. Away from center. Now moving tendency is away from center means when this tries to move away, it tries to slide up along the surface. Right? So when it tries to move away from the center, right? It is trying to move away from the center. So it tends to go upwards the surface with that centrifugal force, with that impact of centrifugal force. So therefore, friction is downward the surface, right? Tendency of a circular motion is always to move away from center. So once this tries to move away from center, since it has an inclined wall, then it will be tending towards moving upwards the plane, upwards that plane. So therefore, friction will be opposite to that direction, that is downwards the plane, right? So likewise, ask questions if you have anything. I can explain anything if you have questions, right? So likewise, if you didn't get anything, don't hesitate. Just feel free to ask any question. No need to hesitate. No need to hesitate. Just feel free to ask any question because all of us are here to learn. No? All of us are here to learn. If your circular motion is perfect, you won't be joining this live session, no? Right? All of us here are to learn. Take it down. Clear. Okay. Good. Good. Very good. Understand what I have done here and take it down. So here this is vertical equilibrium and this is F equals ma towards center. Vertical equilibrium and F equals ma towards center. And from this substitution of R, we proceeded. We proceeded to here, right? So R is substituted from 1. From 1, it can be substituted as mg over this part. Mg over this part, right? So this is from 1. If you didn't get this, this is from 1. This is from 1. This is from 1. Okay, let's move on. The last question. The last question. 20. The last question for the day. Okay. A ball released at point A travels on a frictionless track as shown in the figure. Then the ball just touches point B on the inner surface of the circular part of the track of radius r. What's the velocity of the ball at point B? Right. Velocity of the ball at point B. Point B is here. Right here. Right here. Just touches. That is the word. That is the keyword. That is the hint. That is the hint. Just touches means it's gonna leave the surface that point at that point. Right? That's the hint. It is clearly given as then the ball just touches point B. If it just touches point B, which means it is going to leave the surface at the very next second. At the very next split of time, it is going to leave the surface. Right? Having that in mind, I'm going to use F equals ma towards center at this point. Center is here. Center of the motion is here. So we have forces, reaction acts on this R and mg. Reaction and mg, like this. Right? Now use F equals ma towards center. See? Towards center, downwards, F equals ma. Forces are mg plus r. Mg plus r equals mv squared over r, because now we know that a can be expanded as v squared over r. Right? Now I'm going to state my argument. What's the argument? If it leaves the surface, right, reaction should become zero. If any object leaves the surface, reaction becomes zero. If any object is in contact with the surface, reaction is greater than zero. Right? If any object, repeating again, listen. If any object is in contact with the surface like this, if any object is in contact with the surface like this, reaction is greater than zero, because that is in contact. If any object leaves the surface, if it leaves the surface like this, right? So if it leaves the surface, suddenly the reaction becomes zero, because it's losing the contact. Once it's losing the contact, the reaction becomes zero. Reaction becomes zero. Now I'm going to make that argument, set that argument here. Right? R becomes zero. This is the argument, very important. R becomes zero when leaving the surface. R becomes zero when leaving the surface. Just touches means leaving. Huh? Just touches means leaving. So that's the keyword. Just touches means it is just reaching that point and it's going to leave. Just reaching the point. Just touches the point and it's going to leave. Just touches means leaving. Leaving in very next second. Just touches means leaving in very next second. So therefore R becomes zero when leaves. Right? So make it zero. Mg equals mv squared over r. M to m cancels. So v squared equals gr. V equals root gr. V equals root gr. Right? Now, if you get this question properly, this is a very easy question. This is a very easy question. But if you didn't get the question, and if you try to apply conservation of energy because it's a vertical circle and all that, right, you won't get the answer anyway. Right? If you get the question at once, that is very easy. Now, even though it's released at A, height to A from this lowest point is also not given. So that is a hint not to apply conservation of energy. Now, otherwise, if we have to apply conservation of energy, we have to know these heights. Now, that height is not given. That height is not given. Right? So, root gr for 20, answer is 2. For 20, answer is 2. Take it down. Another good question. There's a good thinking there. The thinking is the part here. If you got the thinking first, the answer is a minute away. Or 40 seconds, 50 seconds away actually. Very straightforward. If you got it perfectly. Otherwise, you will keep thinking about how to apply energy and all that. Right? So get this experience. Get the experience. If it leaves, this is a very important argument. Very important argument. Not even for circular motion. Right? Anywhere in physics, or even if you are doing If you are doing combined maths, in maths also, we are using the same arguments. If any object leaves the surface, reaction becomes zero, right? Okay, so I hope it's clear. Yes, students, any questions? Students, any questions about the MCQ discussion today from circular motion? Any other questions? Anything you need to clarify? Any questions, students? Or if it's clear and if you don't have any questions, just say it's clear, because then I know that you are on track from the beginning. Right? So if you have no questions, you can just say no questions. Right? And if you didn't put anything into the chat box also, I'll assume it has no questions. Right? Yeah. Good, good. No questions. No. Okay. Right. Okay. Then at here, I'm going to wind up the session now, because now we have come to the end of the session of the MCQ discussion of circular motion. And another small announcement. Again, I'm planning to hold another YouTube live session on graph plotting in physics, A-level physics, right? So there I'll be discussing about everything that you need to know about plotting graphs in A-level physics, right? That is very important when it comes to MCQs, because 10 graphs from 50 MCQs are coming in your paper. And when it comes to structured essays also, in structured essays we are plotting graphs. In each and every structured essay we are plotting a graph. So therefore it's a must know thing how to plot graphs. So therefore the dates are not fixed yet. Dates are not fixed yet, but sooner I'm planning to have that session on graph plotting. So you can get updates through my groups. You can stay connected with my Telegram group, Telegram channel actually. With the Telegram channel, I'll be posting everything in that Telegram channel. Right? Okay. So that's it. And I hope you got something from this discussion. We discussed different types of circular motion questions. It covers actually everything. It covers every types that you need to know. Statements, calculations, and in calculations also different types: horizontal circles, vertical circles, springs, elastic strings. There were different types. So therefore, I hope you got something from this, and take this knowledge forward, carry this knowledge forward, and do more questions, and fine tune this skill you got today, and fine tune your circular motion. Right? Then again, you don't need to worry about circular motion. So likewise, part by part, you can polish up your parts in our syllabus and get ready for the exam. Right? So it doesn't matter whether you are a 25 student or 26 or 27. Right? So we will need these things for physics. And if you are a math student, you have circular motion in combined maths as well, right? Okay, so then that's it from my side. If you are a newcomer and if you join this live today for the first time, you can join with my Telegram channel and stay connected for the future updates, because I'll be posting recorded video series and short videos and these kind of live sessions to deliver you what you need to know here in A-level physics, right? Okay, then I'm wrapping up the session here. Thanks for joining. Thanks for joining all and wrapping up the session. All right, then stay safe. Good night and goodbye.